Okay, well let's go ahead and get started. Okay. So hi folks, my name is Mike Walker and for XVB Systems, and today I am going to be explaining explain plans. So I'm going to be getting into some detail on what's in an explain plan, how you get them, and especially some things to look for in terms of performance tuning. So the reason I decided to do this presentation today was that recently I've been working on a lot of query tuning with people, and have found that some of the nuances, if you like, of the explain plans are not clear. And so I want to go through some of that and show some details to look for. What I do find is that people, when they're looking at an explain plan, they'll see, hey, there's a sequential scan on a table, that's my problem. And yes, it may well be, but there's often a few more things when we're looking at the explain plan that I think we should be looking at. So first of all, an explain plan or a query plan tells us how the database is going to run a particular query. It'll tell us the order that the tables are being used, being accessed, how they're being accessed, whether it's a full scan or an index read. And if it's an index read, it'll give us details of the particular index that's being used, how the tables are being joined. It gives us a lot of information. And a query plan is probably our first step when it comes to tuning a slow query. We'll want to get the plan and start analyzing it to find out, where in this query is the slow part, and we'll find out the details from that query plan. So here's what we're trying to get to. Here's just a simple query plan. There's two parts to it. We've got the initial query that we're running. We've got the plan, which shows us how that, in this case, how a table's being accessed. This is followed by the query statistics, which is really, really useful. This will show us where the time was spent and the records that are read. And we'll get into all of this in much more detail. So let's start with how do we get the query plan? So there's some simple SQL commands we just include, like in DB Access, for example, to say, all right, we want to start capturing query plans, or we don't want to start, we want to turn off query plans. And we use these as follows. So if we've got a simple query and we want to just grab the explain plan for it, we'll issue the statement set explain on. So as soon as that statement is executed, from then on, all the SQL that we run, an explain plan will be generated and will be saved off. That'll happen until we end our session or we issue a command set explain off. Now, by default, the query plan will be written to the file sqexplain.out, and that'll be written in the user's current directory if you're using Unix. But if you're accessing the database through a client application, the plan will be written to the home directory of the user running the SQL. Something to note is that the explain plan will be appended to each time. So if you're running multiple statements or running the same statement multiple times, you just need to like tail the explain plan there so you can just keep an eye on the end of the file and see your latest plan. So by default, as I said, the file written to is sqexplain.out, but we can change that by using the command set explain file to, and then in quotes, the name of the file we want to write to. And this is normally what I do. I'll just name the explain file to be the query name with .exp on the end. And because all I'm interested in this case is the query plan and not the results of the query so much, I'll put an output to dev null right before the query, because so then we just get rid of the results, we just get the query run, we'll put a time in front of it so we can get an idea roughly how long it takes, and then it will produce the file here, slow1.exp. And that will have all my explain information in it. If we take a look at it, we're seeing our query here and our explain plan. Now, what follows that, which is really useful, are these query statistics. Now, I'll note you'll only see this if in your onConfig file, you have explain underscore stat set to 1. If that is not set, or if it's set to 0, you'll get the query plan, but you won't get the query statistics. And there's a lot of value in these statistics, so I would recommend you have that set. Now, um, if you want the query plan of like an update or an insert or a delete statement, uh, you may not want to actually execute that statement and change the data. You just want the query plan. So you can set explain on avoid execute, and that will still give you the query plan, but it won't actually run the statement. Um, I'll often in a statement like this, I will change the update to be a select statement, just because I don't want to run. I want to make sure that no update or insert or delete is actually executed. But you can get the plan of your these kind of statements um, without running it by using this avoid execute. Now, when you do that and you run your SQL, you'll see that no rows have been changed, which is good. And you'll get this warning message, hey, avoid execute has been set. So that's why there's no data. If you When using avoid execute, though, you obviously won't see the query statistics because that is only produced after the query is executed. There's another way to get explain plans, and that's dynamic explain plans or dynamic query plans. If you're looking at your database and you see there's some a session running and you want to get some insight into what might be happening and you want the query plan of a running session, you can do that with an on mode dash capital Y and the session ID. And then there's a parameter at the end. One turns it on, the query plan's on, and you'll get the plan and the statistics. Two is only if you just want the plan, and then zero to turn it off. Once you've set dynamic query plan with the on mode, you'll see it under onstat-mysg SES or onstat-mysg SQL. You'll see that the dynamic explain plan has been enabled for that session. The name of the output file containing your plan and maybe your query statistics will be sqexplain.out, but then with a session ID on the end. Now, this is a little limiting, the dynamic query plans. I prefer to capture the SQL and then run it uh, just in DB Access or something, because uh, you will only see the query plan output when the database moves on to the next statement. Now, I know there's a change request so you can actually see this, but currently you'll only see the query plan when it moves on to the next statement. And a lot of the stuff I do when I'm monitoring systems, we see a lot of prepared SQL, with the question marks in. And so it's kind of when it's all been prepared, you won't see the full plan or you won't see the SQL there. It's just kind of limiting. And I've also had issues. I've set the dynamic explain the query. A process is running, issuing a lot of queries, and they're all being put into the explain file. But I've been unable to turn off the dynamic query plan. I issue the statement, but it has not turned it off, that file keeps getting written to and it can get kind of big. And it will keep getting written to until the session ends. That's my experience. But anyway, it's for completeness, dynamic query plans are available. Now, when you look at a query plan, especially for a complicated query, there can be a whole lot of stuff in there. So let's break that down. And this is kind of what you will see in the explain plan. If you're using views, the explain plan may start off with a create view statement. We'll talk about that later. But then you'll see the query that's being run, your SQL for that, and that will be followed by a few status lines showing the estimated cost, the estimated rows returned, whether temporary tables are being used, and any directives. And that's useful to know if your directive, your optimizer directive, is actually being used. It may say, okay, it's set, but it's being ignored, and it'll tell you why. So then the first table that is accessed will be shown, and it will show you the name of the table or its alias and how the table is being accessed, and that's usually sequential scan or using an index. Then filters applied, uh, if any have been used while accessing that table, will be shown, followed by index information. If an index was used to retrieve the data, it will give you the name of the index and other information about the index. So that's the first table hit, and that will be followed by your second table. Uh, Same information, the name, how it's accessed, indexes, filters, and so on. After each pair of tables will be the join. So that will often be a nested loop join in many cases, and that will say, hey, I joined the results of table 1 and table 2 using this method. Now, if there's multiple tables, then you'll see that repeated. You see table 3 and then followed by the join method. If your query contains subqueries, then they'll be placed at the end together with the explain plan for the subquery. And query statistics will be shown at the end of your query and again after subqueries. Okay, so there's a lot there. So let's take a look at an example here. So we've got a simple query joining a couple of tables. So here's our SQL that was submitted to the database. We got our status line saying estimated cost, estimated rows returned, and in this case, a temporary file was used. So we could do the order by. Now we see our first table, and we can see, yep, this table was accessed with a sequential scan, and a filter was applied to the data that was read. The second table was read with an index, and here's information on the index. Now it's read two tables. These two tables are joined by a nested loop join. And if there's more tables, those we just continue like this. Um, The order in which the tables are listed in the explain plan are in fact the order in which the tables are read. So we know we started with this table C and we went on to table O and so on. Now looking at the query statistics, first glance we're like, okay, there's a lot of numbers here. So, you know, what are we seeing and how is it useful? So it starts off with a table mapping. Each of the tables used in our query will be listed together with the internal name is normally like T1, T2, T3, so on. So this will show you our mapping. Now here, because we used aliases in our query, we see the alias name, not the full table name. So I think C was customer and O was order, perhaps. So these T numbers are then used in the information below. So we see our first table, T1, which maps to table C. We see that this row was accessed first, and that then all the numbers to the right apply to the access of that table. That's followed by a second table and the statistics for that table alone. The next section is the details of our join, so giving us our time and estimates and so on. And then lastly, in this example, we're seeing our statistics for the sort. So each set of lines here relates to one part of the query that we see in the query plan. Now let's start looking at some of the numbers we see here, because as I said, it's quite a jumble here. But think of it like a grid. So we start off with our operation. Now, here we've got our two tables that have been accessed, followed by a join, followed by a sort. So this is telling us, what each line represents, or these numbers represent. Now, something that might be a little confusing is that we see a type of scan regardless of whether the table was accessed with a full table scan, a sequential scan, or an index read. Because it's trying to say, look, this is an index scan. So scan just means table access, really. Now, the duration here, or these time fields, are very useful because this is what we can use to identify where is the slow part of our query. So here we see the time taken to access each of the tables, the time taken for the join, and the time taken for the sort. We see rows scanned here for these are for our table access. And again, it says scanned regardless of whether an index or a full table scan is being used. But this tells us the number of rows actually read from disk. With our table accesses, we also see the number of records produced. This is the number of records that have passed through the filters. So we've read this many records, we needed this many records. That's how many records pass on to the next step. The rows returned, down here, it shows us rows produced for our join and for our sort. So this shows us in our joins how many rows were actually joined successfully when joining the previous two tables. And at the end, we've got how many rows ended up being sorted. We had our rows constructed, which I didn't highlight here, but it's showing, okay, we had 297 rows come in, we sorted, and we ended with 297 rows. If we were doing a group by or a count, we would expect our final rows to be lower. Now, getting into these times in a little bit more detail, this is a different example here where we're joining three tables in our query. So I'm just going to highlight these times here. The times for the table access are the times taken just for that table access. So for example, we see for our T1 table, at the end of this query, we spent just under 4 seconds reading from this table alone. We spent over 6 seconds reading from our second table, T2. And then we spent another 6 seconds reading from our third table. These times are not cumulative. They are the times taken just for that access. Now that's different from what we see in the other operations, the joins and the sort. These times are cumulative. So what we see here, we spent almost 4 seconds reading the first table, 6.6 seconds reading from the second table. Our join time is not just the time taken to join this, but by this point in the query, we'd spent just under 11 seconds to read from the first table, to read the second table, and then to join them. And then we add on another 6 seconds for our third table. And so our join at this point is our cumulative time at this point in processing all of this query. So it took 17 seconds to get to this point. And then at the end, following the sort, our 17 seconds here is pretty much the time taken to execute the whole query. So these times are really useful because they show us where was our time spent. And if you're tuning the query, you'd start looking at, okay, which are the lines here with the highest numbers, especially with our table accesses, because that's where we want to start focusing. Another nice thing about these times is, especially for sub-second queries, if you're tuning a query and you're just timing the overall time, you may not know that part of the query has gone from 0.5 seconds down to like 0.2 seconds. If you're timing the whole query, you'll see the time taken for DB access to spin up, perhaps, to connect to the database, to output the data, to write the explain file, all of those overhead parts that if you're running a big long running query that takes many minutes or hours or whatever, then that kind of time is immaterial. But if you're running really quick queries and trying to tune them, the time that DB access takes to run, that overhead will really kind of get in the way of tuning, because you go, okay, it took zero 0.9 seconds, it took zero 0.6 seconds, it took 1.1 seconds. And because you're just timing, you're including all the overhead. These numbers here are the numbers to use to get the exact timing of each part of the query. So let's look at the ways the tables are accessed. And the most common ways we'll see are sequential scans, where we read all of the rows in the table, and an index read, where we're reading the rows via one of our indexes. Now, people see an explain plan and they see a sequential scan, and the common school of thought is sequential scans bad. That must be my problem. And yes, it may well be, but you won't know until you take a closer look at the query and especially the query statistics. Now, scans are not bad if you're reading all of the rows in a table. Reading all of the rows in a table, a scan is the way to go. In most cases, depending on how many columns you're reading from the table and so on. But that's normally the best way to read it. Or if that table is tiny. Often there's little lookup tables that may just be a handful of rows or single rows even. Scan on that is going to be better than using an index. So, and that's because when you're reading a row using an index, while you might target the records very accurately and very quickly, you often need to make a jump to the data page. So you found the row by drilling down through the index, but now you're like, oh, I need these columns. I've got to go over to the data page to retrieve those columns and then maybe filter them and so on. And there's overhead with that because you're ending up doing more reads. So if we, a little picture here, sequential scan will just sit there and read all the data pages, right? And maybe that's too many, or maybe you're reading the whole table is what you want to do. If you're reading indexes, you may end up reading fewer index pages than all of the data pages, but you've got to add in all the access time to jump over to the data page to read the rest of the columns that are not in your index. So to determine if the sequential scan or the index is the way to go, you really need to evaluate how many rows are actually needed. And the query statistics will give you that. We'll come on to some examples. Now, a full table scan can be bad if the table is really wide and you're reading a lot of rows, because you end up replacing a lot of the data that you've stored already in your cache, in your buffer pool, and you end up pushing out a lot of stuff that might be useful later on. So looking at a query plan for a sequential scan, this is the kind of thing we'll see. We'll see our table is being hit. Here is the first table, and it's being accessed with a scan. And it's followed here by a filter. So the filter is applied to the row after it's been retrieved. So we've read the row in from disk or from the buffer pool, and now we're evaluating it. And we say, okay, does this row meet this criteria? If it does, then it will pass through to the rest of the query. If it doesn't, it will be discarded. So this is where we'll look at these filters and then we'll look at these query statistics. So this is telling me that 175,000 rows were read as part of this sequential scan. Um, those rows were read from disk, but then the filter was applied and we only had just under 20,000 rows come out through the filter. The rest of the rows were discarded. Now, in this case, that's over 155,000 records that we read and we didn't use. And this query took us, or this part of the query took over 2 seconds. Now, we would look at this and we're like, okay, we threw away 155,000 records. That was a waste of time reading them. They were thrown out because they didn't match the filter. What we would want to do here is create an index that is on the column here that is in the filter. If we were to do that, then we'd see an index read and we'd only end up reading 19,991 rows. And that would be the best way to process this query. Now, on the other hand, if the number of rows produced is kind of close to the number of rows read, a sequential scan may still be the best way to read this table, because we're saying, okay, I read this many, I only threw away a couple because they didn't match the criteria. Um, so let's stick with the sequential scan. Now, people often wonder, hey, I've got an index on this column. Why on earth am I getting a sequential scan? There'll be a whole number of reasons. Your statistics may be out of date. The database might think, hey, this table's empty. I'll scan it, rather than, the matter of fact, it may have millions of rows. Um, Although I do normally see an index being used in that case, because the optimizer is smart enough to go, it may be empty, but or I think it's empty, but I know there's an index. I'll still use the index. But one of the most common causes for a sequential scan is that the there may be an index on that column, but it may not lead the index. We've got an index on A, B, and C, and we're saying read from the table where B equals a value, right? In those cases, we usually won't see an index being used. There are cases where it might. But also if you're using functions on the column, if you're using like, hey, convert it to a date or an upper, you won't see that index being used, because the index is built on the value of the column, not on the value of the function, what the function returns. That's unless you build a functional index. Um, and like I saw an example not long ago where trim was being used on a character column. Uh, so we're saying, let's say, read from the table where trim name equals Mike, right? The index wasn't being used on name because the trim uh, was a function applied to the column, and it says I can't use this. Now a trim on a character column, it's just a regular character column, isn't going to serve any purpose, because it's going to trim off spaces on the end of a character column, and that would match with a value anyway. So remove the trim, get the index to be used. Something else I see is the data types used in the query don't match the data type of the columns. Uh, so if you're if you're querying uh, an integer column and you're passing in a character column that contains a number, you may not see the index being used. The optimizer can sometimes figure it out, but just take care that those data types do match. I saw an example a couple of weeks ago with a stored procedure. And it was a very simple store procedure, doing an update, saying, update this large table, set column equals this value where whatever, right? Uh, so pretty simple, but it was slow. So I got the explain plan. What I found was that and it was doing a sequential scan, which explained why it was slow. But I'm like, why? This is indexed nicely. Statistics are up to date. I eventually found that in the store procedure, the arguments passed in were defined as n varchar. So the n varchar is for non-case sensitive values. Um, and the database wasn't set up as non-case sensitive. So the n varchar, I mean, it's still, was valid in terms of passing a value to the store procedure, but the table that it was where the column was being used in a where clause was defined as just a regular character, or I think it was a varchar, but not an n varchar. So the optimizer said, okay, these are different data types. I'm going to have to scan the table, and that's what it did. So just changing the store procedure and setting the arguments to the store procedure to correctly be varchars eliminated the sequential scan and allowed the index to be used. And it ran instantly. Okay, so looking at indexes, uh, there's a lot of information in the explain plan when you look at an index. So I think it's easier to show it with an example. So we see here index is being used on table S. S is the alias, and we're showing an index path. Now the name of the index used was, in this case, snapshot IDX5. And uh, the columns it's defined on, we see it's on instance ID and snapshot ID. We also see that snapshot ID is defined as a descending value in the index. The serial says, hey, we're not using PDQ. I'm just going to one thread just going all the way through the index. And the fragments show that this is not a, in this case, it's not a partition table or fragmented table. We're reading all the fragments. It's one in this case. Now, this is followed by the filter we're applying. And we can see here that when using this index, we're using a literal value for instance ID, which is 38. So that's great. You know, it's our first value in our index. Literal value should be efficient. But the snapshot ID is being retrieved from a subquery, and that would be displayed later in the query plan. Looking at another example, here we're retrieving rows from a table where we've got a between. Or this could be, you know, A is greater than and less than values, but here I'm using a between. What we see in the query plan, we're using it being used. And here we've got our lower index filter. We'll normally see that. So this gives our lower bound of reading from this index. Now we also see an upper index filter, and this is good. This means that the database can go through the leaf pages in the index. It can start at 10, it can end at 20,000, and just read all those values. And we see here in the query statistics that we read just under 20,000 rows, and the rows produced is the same. That's because the index is being used. There is no additional filter to eliminate rows. So you can consider when you're using indexes here or you specifying values, if you can supply upper boundary, then the reads might be more efficient. Now, in this case, we've got a filter. Now, this is different from the lower index filter that we'll see. The lower index filter is used to get way through the index to find the rows that match that particular filter. This filter is applied after the row is retrieved. So index was used to get the row, and then this filter is evaluated. So we retrieve the row and like say, hey, is the effective date greater than the date here? If it is, then it will pass on to the next part in the query. If it's not, guess what? Gets thrown away, gets discarded. So this is a case where we look at the query statistics, we look at the rows scanned. Okay, so scanned, still an index read, and we read 7.6 million rows from the index, but only 1.18 million made it through to the next step. So we know that the rest of those rows did not match this criteria. Now, this is the kind of thing we look at this and we make a determination. We should try adding effective date to the end of the index. That way, we only read the rows that we need. And we don't have this additional filter just discarding rows. So this is going to result in fewer reads and therefore faster. Now, I'm suggesting putting effective date at the end of the index. And why is this? It's because it's an inequality. We're saying the effective date is greater than a certain value. So if we do not put this at the end of the index, we won't get the most efficient read, because here we want to go in by the ID value, and then just because of this inequality, this greater than, we just then want to read all the index pages after that value. Another example here of a filter being applied, and remember it's applied after the row is read, is the simple flag, notify email. It's either yes or no. What we can see right away from the query statistics is that we read, was this 830,000 rows? We produced 0, right? That meant Oh, that means that every single row we retrieved with our index um, failed this filter, if you like, and we read it, we didn't need it. So this is a clear case. Oh, and this took 6 seconds. So in our query, wondering why it's running slowly, 6 seconds was spent just on this part to return 0 rows. So this is a clear case where we would want to add the notify email uh, column to our existing index. That way, we know right away that no rows will be retrieved. So our rows scanned will be 0 and it will be instant. In this particular case, we'd want to look at the data and say, well, maybe we should just partition this table. And that may be more efficient yet. Now, looking at index filters, and these are the filters applied after we've read the row. Uh, just like with sequential scans, we might be like, why on earth is this column being applied in the filter rather than being retrieved from the index? And just like those sequential scans, same kind of reasons. If we got a function uh, being applied to that column, again, it won't be used when drilling in the index. We'll read the row and then have to evaluate it because that's when the function will be applied. Now, in line with that, when we're looking at a query and we're applying an operation, if that operation is applied to the column, the table column, then it will be evaluated for every row retrieved. The row will be retrieved and then it'll apply the operation and then it'll apply the condition. So a case like this, for example, where we're adding 3 days to a bill date, it will end up using a filter, an index filter, but that operation will be applied to every row retrieved. And that's going to slow us down. If instead we apply the operation to the literal value, then that operation will be applied one time only, right? It will be calculated. Um, and then we can use the column in the index to drill down much faster to the data we need, and we don't have the overhead of applying that function every time. So in this particular case, we will not see the filter, the operation is evaluated once, and this is going to run much faster. Okay, partitioned or fragmented tables. If we're using those, that will be shown in the query plan, and it'll show us when we're using fragment elimination, which is really useful. So I've got a case here where we created a table. It's fragmented, but in this case, it's fragmented by range and interval on the column receive date. Okay, so there's the syntax there. We've got a rolling window of 365 fragments, la-di-da. Um, our index is not on receive date, but is on these two other columns, store and department. Now, in our query, we're specifying those two index columns, and we're also specifying our receive date, which is what our partitioning has been defined upon. When we look at the query plan now, we see all this extra stuff. So we see the index being used, which is perfect. And then we see the fragments clause. And earlier on, those examples showed fragments all. In this case, we're seeing the 10 fragments or 10 partitions that this query decided to read, because only these 10 match our fragmentation scheme or our partitioning scheme, which is based on date. And we're looking for a range of 10 dates. So we're seeing our fragments that were used here, and here is how we can confirm that our fragment elimination was used. And that's how it shows up. So in the query plan, after each index, you may see the words key first in parentheses following the index. And this is telling you of a potential tuning opportunity. Not in every case, but it's something worth looking at. What this is saying is that, okay, an index was was used, sorry, to retrieve the data. Uh, but you've supplied some columns, but I also need a value which is in the index, but it's not in the sequence of columns in the index. Essentially, we're skipping a value. So in this example, if we've got an index on A, B, C, and D, those four columns, and the query is saying where A is this, and B is this, and D is this, but it doesn't specify a value of C, then we cannot we will use the index, but we can't use it as efficiently as if we had a value of C or as if D was preceded the C. A lot of letters. Let's look at an example. Yeah, this is a real example here. So here we're reading from the table. Okay, our index is on these four columns: log token, E token, prog token, and prog sequence. Uh, in the query, we've got a value of log token, we've got a value of E token, and we've got a value of prog sequence. Okay, so we're seeing our index being used, and now we're seeing an index key filter. So this is telling us, okay, we read the row using the index, using the two values that lead the index, log token and E token, right? But now we've retrieved the index page. We've had to read the whole index in here. We don't need to go to the data page to get program sequence. We have it in the index, but I can't use it to drill down. I've got it, I've got the index, and now let's see if the row I just retrieved or the index page I retrieved, does it have prog sequence equal to 1? If it does, it can carry on. If not, um, it'll be discarded, right? Just like we've seen earlier. So a key first tells you, okay, I it was good. I was able to use the index. I haven't been able to use it efficiently to drill all the way down. Um, Now, in this particular example, what we were finding was we would always have log token, E token, and program sequence. And we would use that to actually obtain prog token to do a read on the next table, right? That was the lookup for the next table. So we got our key first because prog token is in the wrong order. What we need to do, and what we did do, was to move prog token to the end of the index. So we could use those log token, E token, and prog sequence to drill in and only retrieve the rows we needed. And if we look at this particular example, we see that we read a lot more rows than we really needed. We read just over 1 million records, and we needed about 9,000. The rest failed this key filter because our program sequence is not 1 in this case. And we know that this is only part of a larger query, that just this part of the query took almost 5 seconds. And this was used a lot. Um, so by changing the order of the sequence here, we saved ourselves a lot of time. So another way you'll see the key first uh, this statement here following your index is if we're using inequalities. In that same way, a previous example, the value wasn't specified. If we specify an inequality, then that value cannot be used to drill down in the data. So here in this example, we've got the value of tran ID and item type, our leading columns in our index, but item status is an inequality. We're saying where it's not D and it's not H, right? But because the query actually wants login ID for later on for another join, we'll get this key first here. So when you get something like this, you should evaluate what these index key filters are and say, okay, do I need to move the columns in the index, or can I make these literal values? For example, if you've got a table where it's a flag, it's either Y or N, and you're saying where it's not N, then maybe you could just change it to equals Y. And now that can be used to drill into the data. And there'd be other reasons why you get a key first. Again, functions applied to the index columns may mean that that index can't be used for drilling down. And just as I mentioned earlier, with sequential scans, you may have the wrong data type. So again, that's something worth evaluating. When we're looking at data types, remember you can sometimes get those when you're doing for prepared values with your onstat-gsql or onstat-gses. It'll tell you the value for each of your placeholders. It'll tell you, okay, this first placeholder value was 10 and it is an integer or it's a character. And you can use those to verify that you're using or the correct data type is being used in the query. Now, a key only is also shown in your query plan, and the key only index reads are excellent and they're very fast. What it's telling you here is the index has been used to satisfy the query. We haven't needed to jump to the data page at all. So we're going to have fewer reads and therefore things are going to be faster. Now, to get a key only index read, the index must contain all of the columns needed to satisfy the query. Now, that's not just the columns in the where clause, but also the columns in any order bys, any group bys, and the select statements, and also joins. So in this case, this silly little example here, we've got two tables. We're specifying a value for the filter. We're specifying a column for the join. We've got an order by and our select. In order to get a key only scan of this my tab one, we would need an index starting with B because that's our filter, C for our join, D for our order by, and A for our select. Okay. So we need all the columns in the index and then we can get a key only read. Now to use a real example here, this is a case where we're looking at the query and maybe it's taken a long time and we're like, okay, we're using an index. That's good. We've got our index on quantity and order num. So our two values in our index, but we're not getting a key only scan, right? Why is that? That's because we need to add some additional columns. So now what we're doing here, we're adding in to our index or the column we're using for the order and the column in the select for the same table, this items table. Now what we see is we see these magic words key only to the right of the index being used, telling us, hey, I don't need to go to a data page. I just need to read, I just need to read the index page because I've got everything I need. Now, this may not seem like a big deal, but if you've got this in a query that is doing a lot of joins on this index, then you will see the benefit because each incremental performance improvement in each read will just be compounded to the whole thing. So key only scans are good. Now, one thing that we often end up doing is when we're reading a table that then goes on to join to another table, we may not need any other columns from that table. So we can achieve a big performance improvement by getting that key only scan, by including the column that we need to join to the next table into the index. So here we got an example. We're reading from these two tables. We're starting with this my tab one, and we've got a nice literal value. So the first thing is, hey, well, we're going to index on column A, obviously, because that's going to be used to filter our data efficiently, and it will. But we can get a further improvement by adding the column B to our index. And you see, we're not using my tab 2 anywhere else but to that join. We're not retrieving it in the select statement or the order by. There is no order by, no other filters. So here, by adding B, we'll get that key only scan. we do not need to go to the data page to read the value of B, which would have otherwise happened. And so that would be a lot faster. Okay, moving away from key-only scans, another way a table might be accessed is with an auto index. Don't see this very often, but we do see it. As soon as you see an auto index, it is another indicator that there's a possibility for improving performance by adding an index. So an auto index is simply where the optimizer has looked at the query and said, okay, I need to join to this table at this place, but there is no index on that table. I don't really want to do a scan. I will build a temporary index only just for this particular query, and then I'll throw it away. So quickly build an index and then use that same index in the query to join to the other tables. So when you see an auto index, you can use the index, look at the index key and go, I'm going to go ahead and add an index on this column, so we don't need an auto index to be added each time. Now, we'll come on to views a little bit later, but you'll often see auto indexes when a view is being used in the query. Okay, so that's the way tables are accessed. Either sequential scan, auto index, or index. Now let's look at the ways tables are joined. Most common join method is this nested loop join. So what is a nested loop join? Quite simply, it's like this recursive read of a table where we will join the row with everything found so far with the previous row read. So let's just look at this example. So we've got 3 tables. We're reading from table O first. We're doing a full scan, no filters, no nothing. Then we're going to read matching records from our C table. That's our second table here, and we see they're matching on customer number. So we'll find the first match here based on customer number. We'll read the row from that table, and then we will find all the matching rows in the next table. So that's our join to the following table, finding that matches. We will read all the matched rows from that next table, then we'll go back to the previous table and get the next row from that. Then we'll go find the matching rows in our third table. And once we've exhausted all of those, we'll go back. There's no more rows from the second table. Then we'll go back and read our next row from our first table. So read a table, find the matching rows, and so on. Now, this differs from the other join method you'll see as a hash join. Hash joins work a bit differently, and they're often accompanied with at least one sequential scan. Here we've got several. So what happens here is the whole of one table will be read, a hash key will be built on that hash table, and that will be stored in temporary space. Once we've built all of that hash data, we'll go to the second table, we'll read the rows from that, which can be an index read sometimes, and for each row we read, we'll build a hash key from it, and then we'll try and match it to our row hash table that we just built. Now, hash joins can be a lot faster than a nested loop joint in some cases. And they're normally used in like data warehousing environments where you're reading just a ton of data and you don't need to care about, the speed at which you start seeing data retrieved as you might be in an OLTP environment. Now, they're really good when you're reading just lots of data and you're using PDQ. That really improves performance, and you've got a lot of PDQ resources like PDQ memory, because then you can do all that hash joins and stuff in memory rather than using temp space on disk. So they're more efficient there, but we see these and they're less needed in OLTP environments. You can influence the optimizer as to whether it kind of wants to use a hash join versus a nested loop join by setting opcomp in your Informix config file. If you've set it to 0, you'll see more nested loop joins. If you set it to 2, you'll probably see more hash joins. Okay, it's obvious that updating statistics is important to get the best query plan. If your statistics are out of date, that may be why you're getting bad performance because your optimizer is choosing poor query plans. I wanted to give you an example here of something I ran into recently of where statistics threw me a little bit as to why we had this slow query. Now here in this query, we're reading from a table. We're reading using an index column with a literal value, right? And the data types match and everything. But we've got this first one operator here. So we just need the first record return. And we've got this order by. Okay, so I look at the query plan here, and I was surprised to see that the literal value, which is on this profile token, was being applied as a filter. And remember, that's applied after we've read the row from an index. But an index is being used, but it's on token. So I would have thought, okay, why aren't we going in by using the index on profile token? It'd be nice and snappy. But what the optimizer decided to do here was it knew there was overhead in creating a temporary table for the order by, right? So it said, you know what? You've got an order by here on this token column, and you only want the first row or the first value found. I'm just going to read that index because I know it's already sorted, right? I'm just going to read that index until I find a matching value for your profile token, and then I'll be done. But when we look at the query statistics, what we see is that in order to produce the one record, we read 208,000, and this was consistent. Now, this only took 0.8 seconds, so less than a second. But this is another one of those cases where this query or this part of the query is executed uh, hundreds of thousands of times by the application. Okay, those 0.8 seconds add up. So by updating statistics on both of these columns, profile token and token, and rerunning the query, we now see a query that runs instantly. It read one row and produced one row. But now we're seeing this extra line here, temporary files required for order by. Okay, so we went in, this is what I was initially expecting anyway. We're using the index on profile token. It's looking it up by the literal value, finds the one row, and then it sorts the row, which again takes no time. Okay, so again, when this query is being run hundreds of thousands of times, we are saving ourselves a lot of time. And no changes needed to be made to the query or the indexes. This was just one of those cases where statistics needed to be updated. And by updating them, we improve performance. So it's certainly worth checking your statistics if your query is running slowly. Okay, let's move on to views. Views, I'll be honest, these are some of the most difficult things to try and tune in a query. If you're using a view in your SQL, let's say your select statement, and you look at the explain plan, you may see the beginning of your explain plan starts with this, create view, view name, and then there's all the columns, and in fact, the whole SQL for your create view statement. And that will be followed by the explain plan for just that create view statement. Okay, and all of that precedes your actual query. That follows on. Here's your query, your normal stuff here, and your explain plan. And in this case, we've got temp table for view, and we're doing a scan on it. and we're doing a dynamic hash join. So all of that just means all of the rows are read from the view, so it can then do a join to the data that it's read previously. Okay, so we're seeing again lots of mentions of temp table for view, temp table for view. Um, oh, here's our here's our plan, and here's our temp table and how it's accessed. Now, I mentioned auto indexes earlier. You may well see auto indexes being built for temp table for view. This is a different example here. And again, temp table view auto index. So what's going on here, and why is this taking so long? When you see this kind of thing, what it means is that the view has been executed. Um, so before the statement for your SQL is run, uh, all rows for your view SQL have been retrieved and they've placed in a temp table. Okay, and now when your query is run, it just joins the temp table. Okay, the problem with this is it can be very slow and you can use up all your temp space just because of this. So tuning views can be a real headache. Uh, Informix did add years ago now this IFX fold view, um, and that's a parameter in your onConfig file. And if you've got fold view set, which you should, the Formix or the optimizer will attempt to try and do away with building the results of the view, but take like the where clause and wrap it into your main query as additional statements, so it doesn't need to execute the view. And when it works great, but it does have some limitations. So an example though, when you see that create view, it may not just be the standard create view statement. It will try and put in things from like your where clause. And it'll say, okay, let's use an example here. We're joining a table to the view. Okay, and we're joining by this name column, which is both the table and the view. And now we're supplying a literal value to the table. What you would expect to see at the top of the explain plan where you see create view and then your normal SQL, you would hope to see the same literal value, the same criteria that was entered into the where clause of the main query also added in to the create view statement. What will that do? It will reduce the size of the table that's created and it will run much faster. So this is what you would hope to see, uh, but it doesn't always work that way. So sometimes you have to kind of do a few tweaks here to make your query to kind of give it a bit of a hint. So an example here, the same example, if you don't see that filter being applied to the create view statement, um, what I've done here, I've repeated it. So I'm saying, okay, so filter the table by name as Mike, but also filter the view by that same criteria. And then it kind of makes sure that that gets repeated in the create view statement. It'll run more efficiently, return fewer rows, and hence be faster. Another example, and this is adapted from a real situation where the create view is just taking forever. We had a situation where we're querying our table and we had a subquery. Said, okay, go get the IDs from this subquery and then join using that same column to the view. We found we could improve performance dramatically by just repeating that subquery directly against the column here. So we've got it's the same column we're joining on, just repeat the subquery. So it is changed to the SQL, but it did help us improve performance. Now, another reason you might see that create view there with all the rows being retrieved in the temp table is if you've got a unique or a group by or anything like that that requires that table be sorted, or that the results of that view be sorted. If you can remove the unique or distinct or whatever from the view, you may find that you get a better performance. But unfortunately, there have been many times, or several times, when there's been no choice where to but to rewrite the SQL in the view and embed it into the main query and just do away with the view altogether. I don't really like doing that because you may have business logic in your view, but for performance reasons, sometimes I found no choice. Um, However, while doing that process, going through that process of rewriting the view and merging it into your main query, um, I found that there's other joins that the view might be doing that we don't need, because it's like this general purpose view used by lots of different things, but it may be doing extra stuff you don't need for your query. So you can get performance improvements there. Now, I'm about to wrap up, but just before I do want to go through a couple of situations that I've seen. Um, you know how I've mentioned that when you apply a function like date to a column, it will prevent the index from being used or prevent the index from being used efficiently. So here's a case where I've got date time, and I've got my lower and upper bounds on my date time column, but I'm comparing them against a date. So here we have to use our date function to convert our date time into a date so we can do this comparison. What I found in the explain plan is something interesting. The optimizer realized what was going on and saying, okay, I don't need to do that date thing. I can instead change the literal value that I've got here for a date to a date time. So it takes our effective date and it compares it against our literal value here that's been extended to a date time, and it adds on a day. It adds on a day here. This is clever because we're saying greater than 7/6/2022. Here's changed it to a greater than equal, whoops, sorry, greater than equal, the date changed to a date time plus 1. Okay, now we still see the filter here. So it's showing us what was in the query, but we're seeing a key only read. That meant it didn't need to go to the data page. Everything was satisfied from the index, and this runs quite efficiently. And we can see here only the rows. We read 91,000 rows, and we retrieved 91,000 rows. So the index was used to drill down to get the data. Another case, and I did touch on this earlier, is if you've got an index on the same column used by your order by, then the optimizer will say, I don't need to put the results into a temp table and then spend time sorting them. I can just retrieve the data in the same order as it is in the table. So if I look at this particular example, I'm ordering by this column. It happens to be the same column that I'm using for my filter, so I would hope the index would be used. The index is on that column, but it's defined descending. Okay, so when I look at the query plan, there's no mention of temp table required for order by. I see the index being used, and I see that the index is read backwards. So it's a descending index, but by reading it in the reverse order, I will get the columns in the order that's requested. This order by LH sequence, which is ascending. So that's pretty cool. Okay, just finishing up here. I've gone into a lot of detail here about explain plans. They're your first stop when a query is running slowly. So, you know, take a look at the explain plans and start drilling into like the timings here to find out where the slow part of the query is. Um, and I hope I've explained a bit more detail into like the query statistics and specific things to look for, especially the rows retrieved versus uh, uh, rows used, rows produced. That really highlights where there are tuning opportunities. Now, I've still only scratched the surface. There's other join methods that I haven't covered here, but I think I've covered some of the most common ones. At least I hope I have. Just a word about our company, XDB Systems. We provide all sorts of Informix consulting, migrations, upgrades, performance tuning, and we also offer a remote DBA service where we'll monitor your system and provide on-call support. We offer different packages for different levels of support. Okay, I'm going to open up to questions. I need to. Don't know how.
Right now, does anyone have any questions they want to throw into chat? Right now, there is not any.
Oh, good.
All right, give people just a moment more. All right, Mike, I'm going to kick you off presenting so I can hand it over to Art.
Very good. Thank you
So
very much.